That's good.
As usual, we will start at around 11:10. In the meantime, if you have any questions, please ask.
I was wondering if there's any interaction between row clone and row hammer, because things like the bulk zeroing, you'd be repeatedly accessing one row. Like, could it accidentally hammer its neighbors while doing a bulk zero operation?
Good questions. Anyone wants to try to answer before I answer? So the short answer, there might be some, every time you access, there can be, negative effects of that. But the thing about it, if after that, after you close the row, you refresh it, it's not a big deal. And another problem is, as you said, nearby cells can be affected, right? But if you shuffle things around and you don't allow like a huge hammering, because to get effect of hammering, you need to do it thousands of times, right? Without being cached. And that's not what's going to happen here, usually. So the net effect is it's relatively small negative effect on the nearby cells, although it has similar to any other accesses that you would otherwise do on a massive scale, like if you stream through the same piece of memory, for example. Okay.
I guess my other question was, could you use basically the performance difference between FPM and FSM to sort of try and guess like memory locations?
Good questions. Potentially, yes. There are a lot of those informations about the behaviors, like even without these optimizations, a lot of things about the behavior of the memory systems leak some information that intruders in the security domain can use and were used to exploit the information. Whether that would open another source of that, probably. I think whether it makes things worse, I wouldn't say so, because like the whole notion of hits versus misses already, or row miss versus row hits already opens up a lot of potential problems for the intruders, right? So from the security perspective, if that's what you worry about, I think it might open another can of worms, but I think it's not the new one. It's more or less the same one as before. Does it answer your question?
Yep. I guess an extension of my first question is, do you think it'd be possible for somebody to like basically maliciously attempt to row hammer using the primitives, not just like have it accidentally happen?
I mean, people definitely build a lot of exploits based on row hammer, right? I don't think row clone is at any specific new issue here. So there are like several different generations of row hammer attacks that exist, and people look at solutions to them. Okay, I think let's start. As usual, a request for you, if their surroundings and your internet speed allows you to turn on your camera, please do so. It helps me a lot. Okay, thank you guys. So before we start, a couple of things. First of all, reviews. I think the TA promised that you'll get the previous week review by the end of this week, so you should hear back from him soon. Proposal, I'm finally done with the analysis deadline, so I should be able to review your proposals, hopefully this weekend. And I will send it back to you soon with some feedback. And then literature survey, I think you've seen that we posted the slots for the schedule. So I think most people already took the slots. So we had 5 slots and there are 5 teams, so it should be a perfect match. Obviously, some people will go first. It's every year it's the same thing when you open their available slots. Usually the last slot goes first and so on. So it's a backward thing. So no matter how you do it, it's always the same. But don't worry too much about it. Really, at the end of the day, you're not going to prepare for that for a month, right? So it's a literature survey. So you read the papers, you prepare the review. And obviously, when I'm going to grade that, the people who do it first, I'm more generous. I'm going to show potential mistakes. But the further we go, the people who go last, we're not going to tolerate as much of the mistakes you're going to do at the beginning. So there's a pros and cons for that. Okay, for going early.
So a linear scaling of generosity, or?
It's by case basis. It's like, all these things are subjective, right? Sometimes they're just in a bad mood and then that's it. Sometimes in a good mood, they're very generous. So it's hard to judge. But jokes aside, yes, there are going to be some common mistakes that, not to punish anyone, I'm going to highlight in the early presentation to make sure that people avoid them in the future. And you have an excuse to not knowing about this mistake at the beginning, but if you repeat it once or twice and you keep making the same mistake, then you don't really have excuse. It's the same with reviews, right? The first one where I told TA being way more generous, right, at the beginning, but still highlighting the weaknesses of your review, and then gradually it becomes a bit harsh. Okay, any questions about reviews, proposals, literature survey?
I'm just curious, are we supposed to be getting feedback on the weekly reviews? Because we got one for the first week and then we've just been getting our grades.
Okay, yeah, the thing about it, usually you're not getting their feedback unless there is something bad with your review, but you always welcome, there are not too many people in the class, you're welcome to ask if you're not happy, but you want to understand what was with your review, right? Especially if you don't get, say, perfect score, and want to understand what happened. Feel free to ask the TA, CC me, and he will provide you with, justification. Right. I also remind him to send that to more people. Okay. Any other questions? Any questions about literature survey? Okay. So another deadline we're gonna have, we're gonna, do project, demonstrations. Usually in the previous years were posters. So we like the posters because this way we can invite people from different research groups, different departments even to come and, learn about what you did in this course and ask you a lot of questions. And that worked well. In the current situation, poster session, it's a bit tricky. I don't know whether we can organize it or not. I'll figure it out, probably not. Like, we can technically put 5 posters and keep the social distance, but I mean, what's the point if people cannot come, right? So probably we'll try to do the virtual version of that instead. So you're either gonna virtually present your poster, right? And then I will try to invite more people in the class to come through Zoom. It would be harder to them to convince to come to Zoom because they all have plenty of Zoom meetings already, but I'll try my best. So you get some feedback on top of just me, right? I guess one way to do it is probably having breakout rooms, so that each breakout room is going to have like one poster so people can jump between the rooms. We'll try to figure it out. But right now, the way I understand, it's only the hosts can move people between the breakout rooms. So it's not as easy as in the real setting where people just move around. So I need to think about what's the best way to arrange that. But we want to try it out. The reason why we have all these types of activities, we have presentations, we have posters, we have for paper writing, because that's pretty much what you have to do when you try to submit your paper to a conference, right? You're going to go through the review process, paper is accepted, then you have to write a camera ready, then you have to come and present, and presentation would include a full-blown presentation and a poster, right? So pretty much everything we're trying in this course is a mini version of everything you would have to do normally, you know, with your papers, right? So you get a feeling of everything you would have to do with your research. Okay, so the date for, I usually prefer to keep the date the same as our class. So you already had this blocked in your calendar. So probably around December 10th, we're gonna have this event, right, at the end of the semester. So that's not gonna be like a regular, you know, meeting. We might shift the time a little bit, but I think we had relatively small class, we can figure out the time. Any questions? Okay. So today, so I'm trying to do something new from previous years of this course. So previously, I was still working on the memory on this lecture, but I guess there's more and more interest in accelerators these days. So I decided to try and give a lecture on GPU architecture and programming instead of memory, you know, memory coherence and consistency. And that we'll do later if time permits, right? But probably this slide deck is less polished because it was partially prepared by me, partially by my graduate students previously. So sorry if something is not as smooth as in previous, you know, lectures. So please ask questions. I try to answer everything I can. If not, I'll search the answers and respond later. Okay. Okay, so let's start on the technical stuff. So we'll start. If I'll try to explain what the GPU does, I think the best way is to show 1 minute video. Hopefully, guys, you don't mind. You're not going to fall asleep. It's just 1 minute. So just please watch.
Leonardo, and he's going to paint a picture.
Can you guys hear?
In the way that a CPU might do it, as a series of discrete actions performed sequentially, one after the other. And 3, 2, 1. Let me speed it up. Ladies and gentlemen,
Leonardo 2.0.
When we hit this trigger on this thing, 2,100 gallons of air goes through these accumulators, out these valves, into all 1,100 of these tubes, into these tubes within which the bottom of is a paintball. Each of those paintballs will fly across 7 feet of space and in 80 milliseconds reach its target. Hopefully, when it's all said and done, it's going to paint the Mona Lisa.
GPU painting demonstration. And 10, 9, 8, 7, 6, 5, 4, 3, 2, 1.
Ladies and gentlemen, science class is now over. Thank you.
Okay. It was a little bit of advertisement, obviously, but I hope you guys got the point, right? So GPU is obviously competing with CPU, and there is some significant difference in the way things are done, right? So it's more powerful and more parallel, but there are some limitations, right? But you can see the potential power of the idea of massive parallelism and how it can deliver enormous performance. Today, we're going to look into first part of the lecture, roughly first part. We're going to talk about the hardware behind it. And the second part, we're going to look a little bit into how to program that thing, right? So what is a GPU for people who didn't know? It's a graphics processing unit, right? So essentially it's accelerator for raster-based graphics such as OpenGL and DirectX. It's highly programmable, it's Turing complete, and it's a commodity hardware available for regular users. It's available in the cloud of all different types. So below I'm showing you the two most advanced chip from NVIDIA. That's V100 is the one that's already available in the cloud. 800 is available in a very limited fashion. So for one of our research papers recently get access to that card in the alpha version of the Google Cloud for that, it's called A2 instance. But for the wider public, it's not available, but hopefully it will be available in a few months. I expect a huge demand for it at the beginning, obviously. That's for everything they built. This is how those cards look like. And as you can imagine, they're quite expensive. So they had hundreds and hundreds of LUs. They had tens of thousands of concurrent threads running. And this is that video that I showed you at the beginning, try to illustrate the key idea behind GPU execution, abandoned parallelism. Okay, so GPUs are everywhere right now. So you can look at how they compare with the existing CPU. So and how large or big they are. So essentially, this is how different Intel CPUs evolution from Sandy Bridge to Ivy Bridge to Haswell and so on, and essentially this is how the GPUs progress at the same time. So they started not as a general purpose compute units, as the name suggests. They were started as the necessity to handle a lot of very similar activities to process the screen, right? So essentially it started to support just the displayed operation, a regular 2D graphic, right? I don't know how many of you are old enough to work on these computers. Probably you've seen them at least in some museums. I had the luxury to work on some of these very early machines before x86 generation, actually when I was a kid. It felt a lot of fun back then. Right now, when I look at those screens, it looks ridiculous, like, black and white or grayish scale, and like, what kind of 3D or like 4K you're talking about. That was like a really poor screen that your eyes after a few hours of work really hurt. But anyway, we use them and play with them. Then 1996, a big breakthrough, 3D graphics come up. Then gradually NVIDIA tried to, as one of the major players back then, ATI and NVIDIA were building their fleet of GPUs. There is a register combiner. Big breakthrough in 2001, programmable shaders. As you can see, a lot of things are dedicated to graphics, right? That was their selling point back then. And in 2002, finally, they get floating point support on one of the ATI Radeon GPUs. Do you guys know what's happened with ATI, by the way? Anyone? Where is they right now?
Did AMD buy them out, or?
Yep, AMD buy them out. See, that's where there's a response to the. Yep, and there are like we had used to have a big ATI lab in Markham here. Now it's all AMD, as you can know, and a lot of students, I guess, interns there right now, or intern before. So anyway, so they didn't completely disappear, as usually with these big companies, they acquired by someone bigger and more successful. Then unified shaders was introduced in Xbox 360. Then finally in 2006, the general compute arrived to NVIDIA GeForce 8800. And this is the early, like there is a lot of things that happening afterwards, obviously. And, NVIDIA is super trendy right now, as you all know. They just recently, I think maybe a month ago, a little bit more than a month ago, surpassed Intel in capitalization, right? So they're now the most expensive semiconductor company in the world, if you look at the current stock prices. So clearly they had, tremendous success in different ways in terms of impact. And it's very interesting to understand what did they build into their presumably just graphics engine first that make it useful to other domains. So what is the fundamental difference between GPU and CPU? So essentially at the very bottom, and you're going to see Like, I'll try to be as neutral as possible here, because if you're going to talk to people from Intel, they're going to always try to justify you that CPU is as good as GPU, can do pretty much everything the same, as efficient, right? I'll try to be neutral here and show what fundamentally happens from their computer architecture perspective and what trade-offs you count for. So essentially, GPU uses much larger fraction of silicon for computation than CPU. So the question I have for you, are the people at Intel are dumb and then don't use a lot of silicon for computation? Why does this happen? What did they do at Intel and AMD, for that matter, for general purpose CPUs that make them waste silicon and not use it for computation? Who wants to talk? Just enable your microphone, try to answer. And it's okay to be wrong. I just want you guys to think. So I make statements here, and they're presumably correct, but I want you to try to think and justify why that's true. So what does make you inefficient?
So I would say that because Intel wants to support much more general purpose computation, their instruction set is much larger, and so they need to have a lot more silicon to actually support those instructions and all of the different stuff the CPU can do.
You're coming in the right direction, Mustafa, but I want one step deeper. It's true they're general purpose, they need support other instruction, but the question is, what's really in silicon that make it so wasteful, in a sense? Wasteful in the sense for some applications, right? If you ask Intel, they would say that's not wasteful, all the silicon is utilized. But the question is, what is really that make it not efficient?
Could one potential reason be that for a lot of applications, you have to do things in a serial manner. So even if you have a lot of computations, it's not like you can just run all those computations in parallel. So they try to optimize the processors also to be good for serial applications by having things like serial for example pipelining or branch predictions and stuff like that implemented in processors.
You towards the end of your response, you came very close to it, pretty much that's it. So essentially, a lot of time where silicon is spent in the CPU is not to really do an add or multiply. You do really a lot of stuff is just to support the operation of this add. So you do pipelining, you do register renaming, you do out-of-order execution, you do prefetching, you do branch prediction. This is all doing some stuff, but it doesn't really compute in anything. And that thing might eat up up to 90% of your silicon, really, other than LU. So at the beginning, when people add that stuff, like a control logic and all of that, it seems like, some extra pins here and there. Then compute units are getting smaller and smaller, and those structures, if you branch predictions, were getting larger and larger because you need to make your pipelining survive. So essentially, fundamentally, it was not a big deal when the early CPUs, but then over time, it becomes that the supporting system for you to execute efficiently becomes very, wasteful. It's the best way to think about it. It's like government, right? So at the beginning, it was just one person ruling and things were quite efficient, right? And then as you build more and more, efficient, institutions of power, there is a lot of redundancy here and there and bureaucracy, right? So that's what happened with CPU, our 50, 60 years of evolution, right? So essentially at peak performance, GPU uses an order of magnitude less energy per operation than CPU. And we're gonna go very carefully where that comes from, not to their circuit level, but you get a very good feeling how fundamentally GPU can be better than CPU, right? And that's not an argument of your preference in terms of companies and all of that. It's just really a trade-off that you pick. And this trade-off is not for free. That's the other issue. GPU is always trying to pretend that they are completely general purpose, and they are indeed Turing complete, but good luck running a completely general purpose application on GPU. The performance is going to be terrible, right? So it's not like there's both, camps making false claims, so we need to be careful about when assessing them. But fundamentally, the cost, if you want to trivialize the change, there is a CPU that on average across many applications, you pay that price per op, 2 nanojoules per operation, that's your cost. And for GPU, this is 200 picojoule for op, right? And if you think about GPU, even that, not perfect. Remember, I showed you at some point like a few lectures ago, the cost of a simple 8-bit add multiply, right? Fuse FMID instruction, right? You probably forgot, but when I talk about SRAM and DRAM, remember the scale. So if you do remember, just doing an addition would cost you like 20 picojoules. So even GPU is not perfect, right? It still pays significant cost of support and execution, but instead of losing 2 orders of magnitude in energy, it's losing just 1 order, right, to support this instruction. And some of them is fundamental, as we understand, because you need to support memory system, right? But GPU is doing fundamentally a better job than CPU. So that's a trivial explanation what happens. So CPU is as that inefficient, and then you need to spend a lot of manpower, library power, and all of that to rewrite the application in a form that would execute in a faster engine. Okay, so it's order of magnitude more energy efficient. However, application must meet to obey certain rule and perform well, right? So it's not general. I think I mentioned several times back in the beginning of 2000s, people were dreaming automatic parallelization, right? So that will give you your C code, any crazy C code you can write, and it will automatically parallelize. And these dreams quickly were, evaporate as people realized the complexity of the problem. So essentially, certain level of programmer effort is required, right? And we're gonna learn today what kind of effort is required. And it's not trivial, but it's reasonable. Okay, so what's the agenda for the first part? So 3 key ideas that make GPUs run fast. I'm gonna go over them carefully. GPU memory hierarchy, I'm gonna give you a good overview from hardware perspective. Later on, I'm gonna do the same from the programmer perspective. A closer look at modern GPU architecture like NVIDIA's Volta, memory high bandwidth, logic capacities, application-specific hardware. I'm going to give some hints here about some new and super advanced features that I'm not going to cover in this lecture. If we ended up, however, time, maybe I will give you a short lecture on machine learning accelerators as well. So if you guys are excited about it, so I guess at the end of the lecture, if we get enough people interested to learn about that, I can, find some time and, summarize that in one of the future lectures. If like one of the groups don't fully utilize their slot, we can do it. Okay, so why GPUs run fast? There are 3 key ideas behind how modern GPUs processing cores run code. Knowing this concept will help you to understand GPU core designs, optimize performance of your parallel programs, and gain some intuition about what workloads might benefit from such a parallel architecture and what not, right? Obviously, again, NVIDIA's trying to always create impression that everything can be parallelized, and that's a lie, obviously. So there are challenges, but if you care about your performance and your application is amenable to this level of parallelization, the extra work and effort definitely worth it. Okay, let's look at a very, very trivial compute here, which happens to be extremely important for many modern applications such as machine learning, which is computing a multiple of 2 values plus adding another value, right? So an A, B, and C are not a single value, they can be vectors, length of n, right? So this is the typical code you would write in something like C++ to, essentially perform these operations. You're gonna have vector of A multiplied by vector B through the loop, right, and add elements of C, and then you get an output B at the end. So how a regular CPU would execute this code? Forgive me, I'm not going to use a regular assembly here. I'm going to use some simplification. I say abstraction here, but that would simplify all the encodings, and you would understand x86 ISA is not the most beautiful ISA. It's more like in some countries where there are sanctions like Cuba, they make like old cars run like from 50s and 60s, like still operational, but still look very funny when they fix them without the proper, equipment. So that's how x86 ISA looked like. It was invented like so many years ago, and they keep patching it, and eventually it looks quite ugly. So instead of that ISA, we're going to use a more simplified ISA, more like RISC type of ISA. So here there are move instructions, right? There's loads that needs to read from the array. Then there is multiply and add instructions that's going to take 2 arguments to add sorry, 2 arguments to multiply, then the third argument to add, and then store it in the register of 5. Then that goes into memory, right, into the vector. Then you increment the loop, and then you do a branch instruction. Okay, and this is your typical simplify CPU that has fetch decode logic. It has LU to execute. It has execution context. It's your favorite in order of out of order engine. Most of them out of order these days. This is a huge data cache. This is the last level cache. And this is, you know, out of order logic, your fancy branch predictor, memory prefetch, tons of other structure there. I'm not going to talk about. So that's how it's schematically look like. So essentially, how would you try to get performance out of this type of execution unit? So essentially, when MID is stalled, you just jump to the next independent instruction. So if you happen to be stalled on this, right, and you might be stalled on this because the load is not ready yet, right? So you're ready to execute this, but one operand is still coming from memory, right, which is frequently the case here. Caches are not infinite, like usually, and there are cold misses, right? So you might be bringing the data you've never seen before. So if you stall on that, what is going to do? The whole idea of order for execution, try to jump further and try to execute something else. So it can also be executed out of order through the register renamings. You can do a lot of tricks to try to execute instructions. The whole point here, we really want to LU being busy, right? It was built to be always busy, right? But this freaking memory makes things complicated, right? It's just being stalled and delayed and not bringing data fast enough. So it limits my LU, right? A lot of things that CPU is doing is trying to run this data structures efficient. Out of order engines trying to make this run efficient. For example, pipelining, try to make sure that all these things are parallelized and align well. So all of that is just really built to keep things easy, like branch predictor. The whole point is to make sure that I don't have bubbles in the pipeline. Because whenever I reach this branch, if I don't know whether it's taken or not taken, I don't know where to speculate, right? I don't know where to go, right, for next, iteration. People do different optimizations to remove branches, speculate around branches, but that's fundamentally an unknown here, right? Okay. So what can we do? What if we tell hardware these 2 blocks can be completely executed in parallel? So if I have a way to prove it, or I have a programmer to express it, if I can say that these 2 things are completely independent, can I do better? Well, this is essentially the idea of multi-core, right? Essentially use increasing transistor count to add more cores to the processor. So rather than use all my transistors to keep increasing sophistication of the processor logic, because eventually, as you can think about it, I'm going to face some fundamental limits. I first get the low-hanging fruit. I get their, huge bubbles here and there. Like the first branch predictor that we implemented improved things from, 60% miss rate to 90, right? And then the next grade people improve it from 90 to 95. They were heroes, but they go from 90 to 95. And now to be a hero, like in Intel, they're literally talking about 0.5% of branch prediction accuracy improvement. I mean, it's your choice on what kind of problem you want to work on, but it's clear that the benefit of the idea is diminishing, right? But the question to you guys, if it's so diminishing, why Intel still works at that? They can't be just all dumb, right? Like, why do they pay so much attention to the branch predictor at every single fraction?
May I?
Yeah, go ahead.
I think it's because even a few percent or 1% of branch predictor can increase, like significantly increase performance.
That's correct. The question, follow-up question, why? Why 1% of the branch predictor is so important, but say 20 years ago, it was not such a big deal. People live with like 60%. Yeah, I think Jimmy raised the hand. Jimmy, you're muted.
I'm guessing because they want to approach parallelism through pipelining, where branch predictors are more important.
Absolutely correct. So the pipelining is the right answer. One of the major answers, not the only one, but one of the major reasons. And the main reasons, it gets so much deeper, right? whenever in your undergrad classes, if you're coming from a C background, especially, they ask you to sometimes do the meet, simple 5-stage pipelining, right? That was how the early processor looked like, 5-stage pipelining. Right now, Intel processor can have like 24 stages, right? So essentially, you make branch misprediction, you have to throw away after 24 pipeline stages. So the penalty of a single branch misprediction is so humongous. And this is the reason why I think fundamentally what happens, you really stick to the primitives you have. You really like, I know how to do pipelining, I know how to do prefetching. You keep building them more complex. And whenever someone says something doesn't work, you just keep making it even more complex to cover that special corner case. Hack over hack, increment over incremented, getting interactive, right? This is the rat hole that Intel is somewhat right now with the general purpose CPU. And they had to make the best people in the world hired to try to fix things. As you can see, for quite some time, their benefit between two different generations of Intel CPUs are not super impressive, right? We're talking about single-digit percentage improvement, while NVIDIA keep posting like 2 to 3x speed ups with every generation. And between Intel generation, there's 4 years, and Intel, NVIDIA, I think produces a major update every 2 years and a minor update every 1 year, roughly. Okay, so we are trying to go down this path, and then we want to have 2 cores, so we can execute 2 elements in parallel, right? So we're going for smaller cores. Remember, I mentioned this idea from 90s. I think Kunle Lakatoon, who is now a professor at Stanford, was showing these early experiments where instead of 1 huge monolithic core, I can have 4 smaller cores, right? And that's the trade-off you go for. And for some applications, you prefer the first design, and for other applications, you prefer the second design, right? Well, but why would we stay with 2 cores? We researchers at the end of the day, let's go more extreme. How about 16 cores, right? So we keep going, and that allows us to execute 16 simultaneous instruction streams. Seems like nice and scalable, but as you can imagine, someone has to parallelize our code to run this way. So, and another thing, do we really optimize everything? We just take one idea and scale in this idea, right? We didn't take any other opportunities here. So what are those opportunities? Well, if you look at the code that each of these 16 cores are running, well, if you're doing matrix, multiplications, sorry, not matrix multiplication, just vector, vector multiplication plus addition, right? Different elements in the vector are running exactly the same instruction, right? What does it mean? Well, maybe we are paying a cost of supporting execution of this instruction in execution context that doesn't have to be paid 16 times, right? We are wasteful. So the idea to amortize the cost and complexity of managing an instruction stream across many LUs. Remember, there's a lot of control logic there, like all of that needs to be maintained. So instead of having that, we suggest to use a concept called CMD that I introduced before, right, already slightly. So single instruction, multiple data, right? So the idea is don't try execute things independently. So pay some part of your freedom to execute the stream of applications the way you want, but for that, get some performance and energy savings, okay? So this is the second idea behind it. So essentially, you can get 128 elements in parallel. So, right, so you might have 16 cores, and each has 8 LUs per core. So you can have 128 LUs total, right? So this is schematic the difference. So you ditch some complicated data structures with the control flow, because like every single core still has its own branch predictor, its control flow predictor. Right now, if you say no, everything is just one and homogeneous, right? I don't need to replicate the structures all over here, right? So this is where the trade-offs is going, but you understand it's not for free, right? I cannot have the freedom to execute completely random 16 different contexts anymore. Okay. Now the key important things here, like it seems like you're getting rid of all this control flow, but how are you going to handle branches, right? Branches are fundamental to the way we write code. This is not something we can just throw away in the bin. Like it's very hard to write things completely without branches. So let's look at how this thing is going to execute. Just on one core was like 8 LUs, right? So let's say here we had some unconditional shader code. So like not all code is conditional. Some is unconditional, but some might have conditions like that. What are we going to deal with that? So what's going to happen by default is you have a condition. And for different LUs, remember, it's single instruction, multiple data. It means that you're going to execute the same instruction, but on multiple data. So the condition x bigger than 0 might be either true or false, depending on which instruction you execute, right? On which data you execute this instruction on, right? So depending on the data, the outcome can be different. So some might give you a true predicate, some might give you a false predicate. What would it lead to? So it leads to the case that we're going to execute that, right? And this is going to be discarded, and then we're going to need to execute another path of the branch, and those will be discarded. I think the problem is useful, right? Not all LUs do useful work. This is, not, even though that GPUs are Turing complete, in the worst case, you might get 1/8 of peak performance. And if that happens, you are not better than CPU really. You understand that, right? If you happen to compiler and you wrote the code that does lead to this situation and hardware is not smart enough to fix it, then that's what you get. So having this powerful, fancy GPU that costs $10K US doesn't necessarily guarantee that your code, if it's written poorly, is going to run fast. Okay, so this is the worst case performance. Okay, so let's talk about the CMD execution model on modern GPUs. So it's not called implicit CMD. So compiler generates a scalar binary, scale as opposed to the vector instructions, but any instances of the program are always running together on the processor. For example, if you had execute my function and it executes this function 10 times. So hardware, not compiler, is responsible for simultaneously executing the same instruction on different data in CMD LUs. So this is your job, is to write the code that respects the dependencies, but the hardware will do the rest for you, right? It will make sure things run. If you're going to try to parallelize something on a CPU, you would either have to do it yourself using threads or using some libraries like OpenMP or MPI, but it's the burden of you, of the programmer, to use something. Here, hardware would do it for you. CMD width in practice happens to be, fixed. There were proposals for variable width CMD. I'm gonna ask that question before, but essentially, NVIDIA stick to 32 as the size of the number of threads in a warp, right? So the thread is the minimal unit of, context, but you cannot run a single thread in the GPU. You always run at least one warp, right? Even from the hardware perspective. From the software perspective, even that is too small. You really run one block, thread block, that consists of multiple warps, right? We're going to come to the programming model later. But that's architecturally, your unit of operation is a warp, right? The warp has 32 threads, or if you're an AMD fan, then you're going to have something called wavefront, and you're going to run 64 threads. So both companies really stick to their naming conventions, don't want to agree on anything. So if you're going to read different papers, depending on who wrote it, you might have a different terminology. So don't get confused. It fundamentally means the same thing. Mustafa, question.
Yeah, so NVIDIA is always talking about these CUDA cores. So are those actually cores, or are they basically SIMD LUs?
So the core is actually a bunch of CMD compute units.
Okay.
Okay. Calling them CUDA cores is just yet another way to promote. It's a remnant of early fight between CUDA and OpenCL, right? Since I like to tell you different anecdotes, so I'll tell you one story about NVIDIA participating in the OpenCL standard. So you know that NVIDIA support CUDA standard, but people create an OpenCL standard that was supposed to support, general purpose programming across different GPUs. So NVIDIA generously decided to participate in OpenCL and made everything possible. And as I'm speaking from the people who participate in the consortium, to make sure to kill the standards, or create a lot of obstacles to its existence. So when you hear that OpenCL is lagging behind, it's not just because the people are stupid who build OpenCL. Remember, there's a competition in the market, right? So some people join the consortium just to kill it, right? So those things happen. And I still believe, and a lot of people believe, that OpenCL has a huge potential because it can be open standard, not ruled by one single company. But competition is competition, so no one did enough effort to protect it from unfair competition. Okay, so Mustafa, did I answer your question? Yep. Okay. So as you can imagine, 32 or 64, the problem is still there. Divergence can be a huge issue. And in the early GPUs, it was the main major problem all the time. Poorly written code might execute at only 1/32th of the peak capability of the machine on NVIDIA GPUs, right? And even right now, if you write a code a certain way, compiler might be not enough to fix the problem, and you can get a terrible performance, right? And one challenge is that there's so many levels of abstractions and complications. Sometimes figuring out what happens is a very non-trivial effort. So if you write a poor CUDA code, it's going to run. So I had this debate before with NVIDIA people. Like I still don't like to call I still believe the GPU is accelerator, right? That's my belief. And they had a hard argument with me claiming that they're general purpose, right? So because they are theoretically, Turing complete, but the argument is always okay. I didn't see anyone saying it's going to kind of random program on the GPU, and the answer is like, but we can run it, right?
Should just tell them that PowerPoint is also Turing complete, and then
it's like it doesn't go anywhere, the discussion, but NVIDIA people take it very personal. So just if you ever face this debate about whether it's general purpose or not, so where the argument is between, right? Yes, it's Turing complete, right? But it's not. It's like one of those things is that you can technically use it for it, but no one's saying ever would use it for that, right? So that's where it is, right?
So like CPUs nowadays also have like AVX, right? So they have like the SIMD units. So my question is, is the SIMD on GPUs also basically implemented the same way, just without all the fancy control logic?
So the units that NVIDIA use, they don't call it CMD, it's called SMIT. Fundamentally, it's the same thing. Nobody's going to tell you whether it's physically built exactly the same. There is definitely going to be implementation of differences. Fundamentally, from the programmer perspective, it's the same thing, right? Okay. So from the user perspective, it's CMD units and CPU are similar items as a compute unit and GPU, but GPU has tons of them and CPU has just some.
Makes sense.
Okay. So because CPU, people in the Intel also realize that there are computations that immensely benefit from that, but there's only that much they can add, right? They literally like what they can do it for you. Like say you had a 4-core Intel machine that has 2 threads in it, right? So the width of your CMD is, the most advanced machine is 512 bits, right? So if you divide it by 8, you're gonna get how many items you can execute in parallel, right? So you can execute either 8 or 16, items in parallel, right? On single threads. If you do the math, you had 4 cores, 2 threads, right? For example. So that would give you 8 contexts. You multiply it by 16. This is how many threads you can have, maybe 100. And NVIDIA is going to have thousands of threads, right? Okay. But even on a modern CPU, if you want to get a peak performance, right? There is, I did these manual experiments myself, like 3 years ago, 4 years ago, when I started trying to get the peak performance from like streaming application. There was no way to get it without using vector instructions. There's just no way you can fully utilize the memory bandwidth and get the peak ops from Intel CPU without using vectorization. And when Intel says our stuff is easy and automatically programmable, and NVIDIA stuff requires heavy, complicated programming, it's only partial answer and fair assessments. Yes, you can run code in CPU easier, but if you care about performance, you also need to do vectorization, right? And good luck compiler to do it in a general case. So vectorization is a hard problem. Mm-hmm. Any other questions? Okay, so you see divergence is a big issue. So how do people deal with stalls on in-order cores? Yeah, one thing I didn't highlight enough. Remember, when we ditch these complicated data structures from CPU, we also get rid of out of order, because out of order, huge reorder buffer, register and naming logic. It's also big boxes that takes, circuits, right? So we get rid of it. So essentially everything that executes in their GPU world is executes in order, right? There were crazy papers proposed to do GPUs out of order, but they didn't go too far than academic papers. Okay, so how do we deal? So as soon as you get rid of out of order, the problem of stalls come up, because out of order was created to deal with stalls, memory stalls, right? And then it means that if you use GPUs, you need some other ideas to deal with stalls. So how do people usually deal with stalls in out of order? In order cores. Stall occur when a core count cannot run the next instruction because of a dependency on previous long latency operation. We have remove fancy logic that helps avoid them. So we don't have out of order. Traditional CAS doesn't always help since a lot of workloads are streaming. Remember, the first use case for GPUs was graphics. Graphics doesn't have really that much reuse. You just go through the frame and just stream through it, right? Quickly using the same, rendering operation, right? Not a lot of reuse. So this is why first GPUs doesn't even have L2, right? They just really had stream buffers, right? And stretch that. So the idea here, we don't have these data structures anymore. Cache is not useful, but there's a lot of parallel work. So we can interleave processing of many warps on a single core. Remember, warps is just a group of threads, right? They just block together for simplicity of operation on a single core to avoid stall caused by high latency operation. So essentially, how does the idea works? So normally it would be like that. You execute here, run, then another one executes, run, and so on, right? So hiding stalls, the idea of hiding stalls is to make sure you run something in parallel. So essentially, if someone exhibits, so you have a CUDA core, right? You can write a warp on it, right? This is just to answer, I guess, Mustafa's question. You had a lot of these CUDA cores, right? You put one warp on it, or one thread warp. It depends, doesn't matter at this point. So you put some context on it. It very quickly, because it does a lot of compute very fast, you're going to face a stall of some sort, right? The minute you send a stall, don't make this guys busy. Context switch, run something else. It's like, when you go to circus, right? And, there's all these amazing guys that throw, balls up in the air, right? That's the same thing. That's what we're doing. We're trying to throw 8 things in parallel, 4 things in parallel, right? While one is in the air and running another one, then running another one. So you're trying to hit as many stalls as possible. And then the latency is overlapped. So actually my steady throughput is quite good, right? That's the whole idea. So the idea of the parallelism to hide the latency is very powerful. The whole GPU premise to operate is built on the idea of hiding stalls through this parallelism. Okay. So essentially there's, so during this time, this group is runnable, but it's not being executed by the processor. So essentially the core is running some other group. So this is the key idea behind throughput-oriented systems versus latency-oriented systems that a CPU are. CPUs will always focus on latency, how I can run the single thread as fast as possible. Usually, the association of performance was always latency. If I can run this sequential code faster, then I'm the best, right? And it worked for 40 years until, it turns out that some applications can get a better performance through throughput, right? So potentially increasing runtime of one group in order to increase throughput of overall system, right? So what happens essentially here is that we make each individual warp slightly slower, but we increase the overall throughput, right? So they would become slightly slower because you see there's a period of time when these guys could be running, but you're now running something else instead, right? So you might lose some performance, but you sacrifice the latency in favor of throughput. Does it make sense? Okay. So next problem is storing execution context. So as you can imagine now, I need to store a lot of these balls that I throw in the air, right? Like I have this context, right? If I throw a lot of them in the air, I need to store them somewhere. So consider chip storage of the execution context as a finite resource. So the resource consumption of each thread group is program dependent, right? So essentially, we can have different trade-offs here. We can have large context that would do low latency hiding, or we can have 18 small context with high latency hiding. So all these trade-offs are possible, right? So that's architecture design decision. Okay, the whole point here is essentially those are the three key ideas behind GPUs. You use many small down sliced or slimmed cores, right, to run in parallel, right? So we don't want to fancy big out of order. We're going for a lot of small ones, right? It's like swarms of drones, right? And tag cores full of LUs, trying to feed them all with LUs, not being bottlenecked by like some other data structures, and avoid latency by interleaving execution of many groups of threads. And when one group stalls, work on another group. Okay. Okay, I'm going slowly so far. So we are covered the basics. The next thing would be the GPU memory hierarchy, but we're already at 2 p.m. mark. So let's have a 9-minute break, and I want to see you back at 2:10. Any questions? Okay, so hopefully guys, by the end of this lecture, you really understand how GPUs work similarly to DRAM. Okay. See you in 9 minutes. Okay, guys, I'm back. So as usual, please turn on your cameras and let's continue. Okay, GPUs versus CPUs. How different they are architecturally in terms of different structures we've done before. Cores, caches, memory bandwidth. There is significant difference. Here I'm going to compare not with the latest and greatest. This is a Pascal architecture, NVIDIA GPU, but still it gives you a sense where the difference is. Well, first of all, cores, right? Most CPUs that you would buy right now would have, or the same generation. The Intel CPUs back when NVIDIA GTX exists was typically up to 8 cores, right? And they might have multiple threads, so they had L1, L2 caches, right? This is the typical sizes, and this is L3, huge L3 cache. These days, there are CPUs that are as big as 64 cores, but also GPUs also have more cores. But you see, the GPUs tend to have more cores. They had, a lot of SRAM used for execution context, right? Hopefully it doesn't surprise you anymore, right? You understand they need to context switch a lot of stuff, right? So they need to store this context somewhere, right? And then obviously there's a huge, cache here that's supposed to hide the latency of the memory accesses because the systems are latency sensitive. And this is the memory used. This is the memory bandwidth they have, up to 76 gigabytes per second. Most typical CPUs are around 20 GBs per second. And this is the memory. The most advanced are DDR memory. That's the bandwidth it can give you. It's low latency, reasonably, and you can add many and many gigabytes. Big caches, essentially fewer threads per core, modest memory bandwidth, rely mainly on caches and prefetching to hide the memory latency, right? Because it's latency oriented. How the GPU works, you would see here you had way more memory bandwidth. In modern GPUs, that is another 4x higher than that. Why is that so? Why you need so much bandwidth? Any theories? Why you need so much bandwidth here?
Well, I guess you have a lot of execution context, so like they all might want to be like pulling data. So if you're pipelining it, you need like a lot more bandwidth to pull in all of that data at the same time.
Absolutely correct. So if you had way more workers to do the job, you better be supplying them with the data so they had something to do, right? So that's what's happening here. So you need way more bandwidth. Here, utilizing this bandwidth, as I told you, it's a very non-trivial exercise even for experienced programmer or computer architects. Like good luck. Like if you want to try to write a simple parallel loop that would fully utilize this memory bandwidth. And like good luck. It's like you need a lot of expertise. You need to use, OpenMP, you would need to use vectorization, everything possible. You won't be able to write a loop that would do this magically for you. Here you can utilize this quite quickly. If you are using machine learning and you had a batch norm layer, it's going to be bottlenecked by that right away. So it's just like it's very easy to write a code that would be bottlenecked by memory bandwidth and GPU. That's a trivial exercise. Anyway, so they use a different standard of memory called GDDR5. It has less memory. Here I'm saying GDDR5. Right now they use something called, for the most expensive GPUs, they use something called HBM, high bandwidth memory. And for cheaper GPUs, it's a funny word, but like for something that doesn't cost 10K, but costs more like $1,000, they would use GDDR6 and GDDR6X. That's the standard of the memory. So this memory is high bandwidth, slightly worse in terms of latency than DDR4. Power-wise, somewhat comparable. Okay. So this is architecturally where the trade-off is, right? You see there's no miracle between CPUs and GPUs. They are conceptually similar based. It's just the trade-offs that you decide to go for are different, right? And the applications you're aiming are different. Okay, so this is the, I guess, thought experiment that Serena did. So she was trying to look what is the maximum peak throughput she can get from, the computation we showed before, 2 vectors multiplications plus addition and storing the results. So let's just think about it conceptually. And it's a very good exercise that behind things like roofline models that I don't cover too much in this course, but that's how I like to understand you, how much you can achieve. So if I had 3 memory operations, 12 bytes for every multiplication, right? Then NVIDIA GTX 1080 can do 2560 of these multiplications per clock in a single cycle. That is the maximum throughput you can get, right? At this frequency, right, you would need 45 terabytes per second of bandwidth to keep functional units busy. And in that GPU, you only had 32 GBs per second. Even in the most advanced GPUs 800 that I mentioned at the beginning, they had slightly more than a terabyte per second memory bandwidth. So you're still at 40x over that. So what does this mean? It means that memory bandwidth in a foreseeable future is their bottleneck for compute here. So on computation like that, GPU's efficiency is going to be below 1%. But with all of that, it's still more than 4x faster than the best CPUs we have in the lab, and we have the most advanced CPUs. So and that's the configuration of that one. So it's better utilizing things, but it's still about 3% of the efficiency on this computation. So, okay, I got a question here. Let's see. Compress the RAM. Compressing the RAM is a good idea. It gives you more capacity, but would it give you more memory bandwidth? Well, if you can transfer the data in the compressed form as well, then yes, right? Otherwise, it just gives you more memory, right? Memory capacity avoids accesses to disk, but it doesn't let the memory bandwidth go faster. So you need to compress memory, not the DRAM. And this is why I guess some of my papers was quite useful for GPU applications, right? When I work on bandwidth compression, that has a huge impact on performance of their GPU applications, right? Because the memory bandwidth is the bottleneck for many of them. But you got a feeling, right? Like it's even when people say, oh, GPUs are poorly utilized, even a poorly utilized GPU might still be much faster than CPU, right? And one thing about this computation, like what fundamentally is bad in this, in this computation that I cannot easily think about what you were going to do to make it much faster. So it's what fundamentally is the issue here.
Like, I guess it's just that for like a one multiplication, you need 2 loads and like a store. So
for a relatively cheap compute that costs you 1 cycle to do, you would have to do a memory operations, right? So you either have to go and figure out how to do memory work at the same speed as, LU instructions, and good luck doing that. Right now we're about 2 orders of magnitude between the two. Or what is the other option?
compute in memory. No.
That's a cool thing, but anything else that is simpler than that, and you know this context from this class already.
Keep all the operands readily available?
Yes, so essentially you need to make sure that there is reuse. The reuse is the key. So if I can make such thing that in my computation, right, there is, some reuse, then it's good. So this is a vector operations. If it's completely streaming, there's not much you can do about the reuse. But if you start to think about more complex operations, like a matrix multiplication, then there's a possibility for reuse there. And they also had way more compute, right? If you think about matrix multiplication, right, per dimension, right, you're doing something that, well, not cubic, but way more than quadratic, right, in complexity. For every byte you bring, you need to do way more compute. And additionally, there is reuse. So this is where's the hope. And this is how, say, something like matrix multiplication can be compute bound rather than memory bound, right? So this is why, so essentially my simple mental exercise when I look at the new problem, I first look fundamentally how much, forget about hardware at all, even though I'm a computer architect, which is fundamentally how much memory accesses you do for how much compute, right? And this is the fundamental, this is written in your code, right? And if this ratio is one way or another, it kind of tells you which kind of architecture you want, right? because if it's just linear, you're going to be bottlenecked by memory bandwidth no matter what. In fact, do it like if you try to run a parallel vector addition on a GPU, like just use their, take your GPU on your machine, try to take the CUDA code to do efficient two-vector additions. You're going to be disappointed by the performance. Why? Because the number of computations is linear with the number of memory accesses, right? When I'm going to run it through something like NVProf to profile the computation of that loop, you're going to see that you spend less than 1% computing something on the GPU, and everything else, you just move in the data from the CPU to GPU through their PCIe, for example, right? That becomes your bottleneck. Anyway, the bottom line here is before outsourcing something on the accelerator, think about the fundamental algorithm that's running. That's critical to understand what's going on.
So just a question, is there no sort of like prefetching on the GPU, or like would it not make too much of a difference in this case?
Very good questions. So anyone want to take on the question? Prefetching on the GPU. Should it exist? Shouldn't? It doesn't exist. By the way, I tried to make it to work and I failed. There are people that claim papers that claim to have prefetching on the GPU. And when I ultimately look at the source codes, it turns out they cheat. So and then we can talk about that. But first I want you to think prefetching. Now you guys, is anyone who doesn't understand how prefetching works? Should I summarize? Because what I want you, if you understand the basics of prefetching, why it's a tricky thing for GPUs. It's not impossible, but why it's difficult. Jamie?
Is it because...
Sorry, Alex started to talk. So Alex, you can give it a try.
Is it because you're already being bottlenecked by memory so heavily that it's already like 100% usage, so you don't have time to prefetch?
There are cases, you're not 100%, but there are a lot of cases where your memory bandwidth bottlenecks. What the prefetching fundamentally does, it trades the latency for an extra bandwidth. You read more data in parallel, hoping to bring something useful to cut the latency. But you already have a way to cut latency through running multiple different works. And using something that is not useful might cut the bandwidth, and you might ended up being, losing the bandwidth. What I was trying to do by motivating, this is why some, certain papers shouldn't be published and people should check the code carefully. I read some papers that claim that they're, that they can do prefetching, like from Ascos. And I thought, okay, that's a good idea. Let's try it out and do better, because I felt like their mechanism was not good, but they're clearly showing that it can be done and performance can improve with their trivial mechanism. And then it turns out when I tried it myself, every time I try to prefetch something in GPUs, there are periods when the memory bandwidth is not like 80% always utilized. It's sometimes 20, then it's 100, 20, 100, it jumps, right? The problem was that the phases when it's underutilized are relatively short. It's a certain number of cycles, like say 50 cycles. It was very hard to prefetch this accurately. It's not like there's a big gap continuously. So anything I tried didn't work, and then I asked for the source code from the people who claimed that it worked. It turns out in their simulator to mimic the prefetching on the GPU, which is acceptable, like we all use simulators in the computer architecture field to mimic, they sent all the prefetch requests to a separate non-existent channel. So they didn't mimic the memory bandwidth at all. They just sent all the requests through some virtual channel. So they never had a, back pressure of extra bandwidth. So they cut the latency when they're lucky, but they never paid the price of being wrong, right? This is why I'm a big proponent of their, artifact evaluation in their, in systems community. So when people get their paper accepted, the better be submitting the artifact with their paper so people can validate what they do. Okay, so this was a good thought experiment. Let's move on. So the key takeaway, you got it, right? Bandwidth is limited, right? You very rarely see this on CPU, very rarely. The CPU, the whole memory stack is built there that you never hit the bandwidth wall. You might have the memory wall in terms of latency, but not the bandwidth, right? But GPUs are a totally different beast. Tons of compute can easily get out of bandwidth. So, so no amount of latency hiding helps this thing. So bandwidth can be a bottleneck. So bandwidth is a critical resource, and actually fundamentally, it's very difficult to get. You would see people are just right now paying the cost for it. So it's like NVIDIA really needs to top memory bandwidth, and they are, the best GPUs. They had to buy high bandwidth memory, which is extremely costly, right? So Micron and Samsung are happy to supply that, but it's extremely costly thing, and also very power costly. Okay, so you need to be smart about that. You want to organize the computation so you reuse the data previously loaded by the same threads, and try to use the memory hierarchy as efficiently as possible. Share data across threads, so the scratch part is a good idea. So all ways to avoid, extra memory accesses, not in terms of latency, but in terms of bandwidth, is very critical on the GPU. Okay, so this is just, a little bit of terminology for you to understand what the GPU has. They had on-chip register file so that register file is determined by compiler. So compiler on NVIDIA, it's something called NVCC compiler that was going to compile your code to run it. It does the register spilling. Again, I didn't have time to talk about register allocation in this course. There are a lot of important topics I cannot cover because that would be a full-blown undergrad course here, right? But essentially, you know about registers, you know about register spilling if you take the compiler classes before. So here, the compiler will take care of that. Sometimes was doing some mistakes in register allocation in terms of performance, not in terms of, not properly mapping. So the shared memory that programmer managed, there's L1 cache. In the most advanced modern GPUs, they even figure out, because fundamentally it's all SRAM, right? Remember we learned about SRAM? It's all SRAM. They turn out to make it programmable. So some applications want scratchpad. Scratchpad is something that you manage, right? It's like you think about it, the cache, but there's no explicit management policy. You need to push and pull things from scratchpad. It's completely your responsibility, but it's not going to make dumb replacement decisions, right? Because if you cannot, like the cache comes with whatever replacement decisions are there. So, but the problem was there's fixed budget, and they always give in some budget to scratchpad, some budget to cache. Right now we make it programmable, so you can use some cache for scratchpad and vice versa, because the cells of that design, they're all SRAM cells, so you can actually make it happen. Okay. Off chip, we had an L2 cache. The reason why a cache, which is slower, obviously, so the compute cores, the registers, there's L1 cache here. Remember, nothing in GPUs is super optimized for latency, right? So when you're going to look at the memory latency or L2 cache latency, you might think everything is super fast on GPU. You might be disappointed. It's actually slower than on CPU. And why it's okay? Because we're not latency bottleneck. Everything is optimized for bandwidth, for parallelism, right? Parallelism is the key here. L2 cache, as I said, it was not always there. It's still relatively small. The reason why it appeared is when people start to use GPUs beyond graphics. So it turns out there are other, patterns of accesses. There is reuse. There's temporal and spatial reuse. So people start to benefit from L2 cache, so they added it. And there is something called device memory. So device memory is, there are several aspects of it. There is global memory, texture memory, local memory. So all these different names. At the end of the day, it's DRAM. It's based on DRAM, right? And the way L2 cache is, it serves as a bandwidth filter for DRAM. So you try to filter out some accesses rather than reducing latency. So you see, fundamentally, L2 cache here as a structure used differently. Instead of trying to reduce latency for CPU, they had a different way to reduce latency. It serves as a bandwidth filter. So replacement policy, the organization of these caches can be quite different because the goal is different. The goal is filter rather than, cut the latency, right? So they optimize differently. Okay, so this is register file. It's per thread. There's a shared memory here that I say it has a little bit slower. In practice, it's almost the same. It's per thread blocked, and this L1 cache. Okay. Okay, and this is how, I guess, slides are from last year. So this is how the best GPU looked last year, right? So right now it's a little bit different, but fundamentally not that much. So 21 billion transistors on more than 800 millimeters square, 80 SMs. So this is your CUDA cores, Mustafa, right? So simultaneous multiprocessor. Sorry, this is simultaneous multiprocessor. The CUDA cores are the small pieces inside of them, right? This is called CUDA cores, and those you have 5,000, right? So these CUDA cores are the best counterpart for the CPU cores, right? So when you compare the cores, right, that's what you're looking at. This is the smallest granularity of the core, right?
So like each of the cores has its own like execution context and stuff like that, or?
So each of them has its own, they can run a separate execution context, yeah.
Okay.
So you can context switch in them, yeah. And there is also a lot of tensor cores, right? You see this. So tensor cores are used for, you guess it, machine learning, right? So that's what they are utilized for. You can have high bandwidth memory, 16 or 32 gigabyte, depending how much you're willing to pay. This is the memory bandwidth, up to 900 gigabytes per second. And this is NVLink. So several of these big GPUs can be connected with a proprietary NVIDIA interconnect. So they don't use PCIe, right, that we all typically use. That's cheaper, but slower. In contrast, PCIe is around 16 gigabytes per second, right? Okay, so this is how this monster GPU look like. And yeah, that pretty much finishes what was supposed to be a first part of my lecture. And I want you to review this paper. It's still somewhat outdated, obviously, but what I like about it, because it's older, you can see a lot of predictions in this paper. Again, you can see which of them are true, which are not. And that's coming from Steve Keckler, who is both a faculty and the head of NVIDIA research. So it should be interesting for you.
And what do you dislike about it?
What?
What do you dislike about it?
Let's not go into that. So I'll let you read first. I think it's in general this paper I picked because a lot of NVIDIA papers has too much marketing in this. This paper actually doesn't have a lot of marketing. Okay. Okay. So that was their intro into GPU architecture. And now we're going to talk about GPU programming. Okay, so a lot of the slides, I guess were done by Shore. So they are taken from different NVIDIA manuals and from UIUC manuals on how to program GPUs. Before we go into that, any questions? Oh my God, it's trying to click without me. So let me try to fix it. Essentially using some transitions here. I need to kill the transition somehow. Just give me a few minutes. Okay, hopefully it's not gonna switching without me. Okay, so any questions before we go into that part? So we'll learn about how to program those guys. Okay, so there is no way I can teach you how to well program in CUDA in 20 minutes. So don't expect that. You would need to take a separate course if you want to be a good CUDA programmer. But I hope that at least I'm going to show you which direction to go, right, and where to learn. Okay, so the objective is to learn the basics of API functions in CUDA host code, device memory allocation, host device data transfer. Remember one thing about, remember that my discussion with NVIDIA about whether they accelerator versus whether they are an independent, general purpose thing. As you're going to see how we program GPU, you're going to get a clear feeling that it's still a master-slave relationship, right? And it's a very heterogeneous system because everything is initiated by CPU. GPU can't really do anything without CPU, right? you can see that it still fundamentally looks like an accelerator, right? Even though it might be the main and computes most of the code, it's most important and most expensive part of the system, it doesn't change the fact that it behaves as accelerator. Okay, we had similar example before. So right now we're just looking at the vector addition, right? So we're going to exploit huge data parallelism exists in such operations. And the way traditional C code is going to be written, we're essentially going to have a for loop, right? Which compute the vector sum iteration by iteration, right? And then we essentially have some memory allocation for all these arrays A, B, and C. And there will be some IO to read the data into those elements. And then you call the functions that would do the addition. So how is that fundamentally, from a very conceptual, how it's different is heterogeneous computing using CUDA host code. So essentially, you would need to include some stuff, obviously, at least CUDA.h as the minimum, usually more than that. And then if you want to implement that, essentially what you need to do, you would essentially had similarly 3 arrays, and then you would need to allocate memory not only on the CPU as before, you would also need to allocate memory on the GPU because it's a different device. This is why sometimes confusingly people called one as host, one is a device, and the host is CPU, right? Again, in the part 1, you need to allocate device memory for all of this, right? And you need to copy content of A and B to device memory because that's your, parameters of the addition. The second part, again, conceptually, there's no code here. You do a kernel launch, and that's where really GPU is now running, right? So before you just copy data into it, right? GPU is invoked, but it's not doing anything interesting. This is when the device performs the actual vector addition. Then there is a copy back. So GPU is down in the sense it can only do like a pony with a few tricks, right? But the rest is still done by CPU, right? So this is how it always happens. Like whenever you're going to use accelerators, not just GPUs, any accelerator, and I keep insisting that GPU is accelerated here. So you see there's a host, and it asks the device to do something, and you copy back things with the results, right? It cannot, right, execute the full-blown int main and things like that, right? It's just doing certain kernels.
Can I?
Yep.
So in order for it to become like a full-blown, like general purpose compute, like to avoid this movement of data, would you then have to have GPU use, like share memory with CPU physically, right?
I don't think it's even that is enough. People already did shared memory, and that exists, and there are GPUs with shared memory. I think like some AMD GPUs had shared memory. That's not it. Like think about it. Okay, if I wanted to be general purpose, so right now it's just running a kernel like matrix multiply. You say like, oh, I'm not happy to run just matrix multiply. I want to run the full C code. Well, then you have to execute int main, blah, blah, blah. All of that is single thread. How well it's going to execute it on a GPU? You can make it run, you can fit all this code into the GPU kernel. Okay, you get really poor execution, but you still can run it. Does it make it independent? No, someone still needs to run it. Someone needs to invoke operating system, the thread, the operating system. How are you going to run all of that code on a GPU when you only really run a single thread at the end of the day, right? So we're going to push the boundaries. CPUs can do the boot, right? Bring this data in. Is it feasible to expect that GPU can do it? But yes, you can force yourself and spend engineering effort to run it on GPU, but it's never going to be fast. So it's a coprocessor-like, accelerator-like architecture. It only makes sense to use it when it's good, and it's good for a very parallel code, right? So I don't see fundamentally being a general purpose. You can call it a Turing complete. Yes, it can execute any code, but still, right? Like, are they going to use it this way? Okay, any questions here? Okay, so this is just some reminder about their, the way the memory is organized. But now, since it's a programming model, right, you would have to switch to, say, NVIDIA's terminology, right? But fundamentally, there's still a SRAM, DRAM, and memory bandwidth there, but they had their own, terminology. So there's a host, small box here, which in reality is huge, and this is actually smaller than it. This is CPU, this is GPU device, and device has a global memory. That's GPU memory. Remember, host has its own memory, CPU memory, right? That's two different types of memory using a different spec, maybe somewhat similar technology, right? But same companies build them, but they are organized differently. Then the device has a grid, and a grid consists of units called blocks, right? So blocks are really the units in which you're going to program this thing, right? You're not going to program individual warps. So you're going to express the parallelism in your code in terms of blocks, and the blocks are going to run a group of threads, right? Threads are groups of warps, right? So this is, and each of these threads has its own dedicated register, its own context, and as a programmer, you don't need to worry about. You need to be careful about registers because everything's going to work, but if you're going to write a code that requires too many registers, what's going to happen, surprise, surprise, the number of contexts you can be run will be less because the number of physical registers is small. So whenever a compiler decides how many blocks you can run, it's going to make resource allocation estimation very carefully on what you need to run. And if it turns out you need too many of these, you're going to run way fewer blocks, and some resources will be underutilized. So you might run different number of blocks depending on how many resources you have. So devices code can have read writes per thread registers, read writes in the global memory. Host can transfer data to from per grid of global memory. That's what the host can do. Okay. Okay. So then CUDA malloc. So now we're going, like, I apologize for fans of AMD. I would have to pick with one platform here. I picked NVIDIA's one. So we're going to use the terminology NVIDIA use and their pieces of code because they tend, they won the competition so far. Whether it was a fair win or not is a separate discussion, but they are the winners. So we're going to use that terminology. So CUDA malloc, right? That's the primitive that allocates memory on the device. It has two parameters, address of the pointer to the allocated objects and the size of the allocated object in terms of number of bytes, similar to regular cmalloc, right? Hopefully you're familiar with that. But remember, there is a big difference. This thing is allocated here. So you write this code in, as a part of your C code, right? But you're using some CUDA functions. And when you write this malloc, it's not allocated in here, it's allocated in here. And counterpart, CUDA free, right? If you're not going to free, this thing's going to get out of memory very quickly. There are no great virtualization support in the CPU. You're going to get out of memory much quicker than an operating system like Linux, where if you make a mistake, it can, live with your, wasted memory for a while. That's going to be not going to last here for too long. Okay. CUDA copy, that's another primitive. That's what happens here. It transfers data between the host and the device. It does the memory transfer, requires 4 parameters, pointer to destination, source, number of bytes, and the direction of transfer to or from the device. Transfer to device is asynchronous, but you can imagine that to improve performance. Okay, so how the host code look like? So on the host, that's, if you ask me, that's where the complication is. When you're writing code, you are thinking about one device usually, right? You're writing all the code, you think it's running one by one. What's difficult here, you had pieces of code that's running on one device and pieces of code running on a different device, right? And that's what can be confusing. And some of that you're writing the code that's in between the devices. So essentially, this is what's running on the CPU. This is the CUDA memory allocation, right? Which starts on CPU, then goes to GPU, to the device. And then you transfer the data from what you have to the, to the right place, to the right array. So you do malloc and then copy for each of this. CUDA malloc for C you do, but you don't copy anything, right? Because you're going to copy later on back, right? That's for the result. Okay. And here, commented out for now, is the really interesting stuff that's going to execute on the GPU itself, right? Okay. Okay, and yeah, so that, can you hear me well? There was some issue with the internet, yeah. So in reality, remember, the code is not as simple. There's always error codes that are possible that you need to check for. You can get out of memory easily. Okay, threads and kernel functions. To learn about CUDA thread, the main mechanism of exploiting data parallelism, we need to understand hierarchical thread organization, how to launch parallel execution efficiently, and learning about thread indexes to data index mapping. Okay, this is our example we're going to go through. So remember, what's happened here is it's heterogeneous execution. This is serial code, and so far I only show you serial code. And this is the parallel kernel code. It has this weird syntax, right, with the kernel here, right? This is how the CUDA code is written, right? So you describe the parallel kernel that runs on the device with some parameters to it, and it has some required parameters. So remember, serial codes run on the host, parallel parts run on the device. It has some syntax. So you need to describe the number of blocks and other things. Okay. This is not particularly interesting here, so let's skip that. Okay, arrays of parallel threads. So a CUDA kernel is executed by a grid, and a grid is just an array of threads. All threads in a grid run the same kernel code. This is, single program, multiple data type of primitive. Each thread has indexes that it uses to compute the memory addresses and make control decisions, right? So essentially, each guide, like how each of the thread would know how they're different from the others. They have an index, and that index tells them where to read their data. So you can write a math such that you would skim through this, and each thread would know which index to read from and which parts of the data to read from, right? So essentially, just indexing. In this streaming context, it's very simple. Everything is just, advancing by +1, so it's very easy to write this code. But that's fundamentally what it is. You need index of a block and block dimensions, right? Okay, and essentially this is how each thread blocks. The thread blocks is really the units that you execute. Each of these thread blocks, like that's a big item, it can have many threads on it. Each thread can run on the individual CUDA cores, but the thread blocks can map, like you can only have that many thread blocks because it has limited number of assemblies, right? Okay, so you divide thread array into multiple blocks, right? And thread within a block cooperate via shared memory, atomic operations, and barrier synchronization. Remember, parallelism is amazing until you get races, right? So you don't want to have race conditions. So you want, some synchronizations for most programming. Threads in different blocks do not interact, except for some atomic operations on global memory addresses. Otherwise, everything is isolated and execute on its own part. This is the beauty of embarrassingly parallel code. I can run any part independently, right? If you think about something like summing elements of the array, right? It doesn't matter in which order, which parts we add up. At the end of the day, it's all associated, we'll get the same answer. So it's the same principle here. So each thread uses indexes to decide what data to work on. And so essentially, you had block indexes. So it can be 1D, 2D, 3D. And why it's required, it's required by the complexity of the algorithm. The programmers ask for that, so they add a complex support. So indexes can be very complicated, right? It can be multidimensional. It simplifies memory addressing when processing multidimensional data. It says so, but even coding in 3 dimensions, it's not the easy task, I can tell you. So it's very easy to make mistakes. But image processing, solving differential equations on volumes naturally had this level of parallelism. So the people who use GPUs early kind of pushed the CUDA, the programming language, evolve in the direction of multi-dimensions because they had this abundant parallelism. So they don't want to transform their 6-dimension arrays into a scalar, right? So they clearly had a lot of dimensionality already, but easy parallelize, and they want to utilize it. Okay, so to learn the basic concept involves declaration, built-in variables, and thread index. So this is how the device code looks like. That's the most interesting part. So this is, so remember I told you there is this, global local primitives. There is the thread index, block index parameters, right? That's invoked here. So this is, the function call itself. This is the, the indexes I mentioned. Okay. And this is the actual code, right, that you do. right? But you need to know all these complications because I need to know which data to take, right? That's the whole complication here. And because all these threads execute exactly the same code. So when you look at this, remember, this is executed like many hundred times, right? In different threads, all in parallel, but in different contexts, right?
So why do you need the if I is less than n? Like, I feel like adding an extra branch just makes it less efficient, no?
Yeah, but what is going to happen if you get out of bounds?
Well, like, I guess you wouldn't care because you're only copying back n bytes later, right? So, like, even if it's doing some random like additions, you wouldn't care.
The problem is that if you do an add kernel, you need to provide a primitive that is smart enough to work on all inputs. And here, otherwise, it wouldn't be aligned. So you cannot really access memory that you're not allocated, right? You get out of memory access.
I see. Okay.
There is ways to deal with this if though. This is a simple control flow. Okay. Okay, so so this is device code, this is a host code. So on the host, that's what you do. You had your dimension, you slice your array by dividing by a proper amount. And this is how many threads you want to have in your block, right? So this is how you write the kernel. You essentially give it to parameter. You take the array size. This is how you round things. And then essentially the ceiling function makes sure that there are enough threads to cover all elements. So essentially on the host, you're writing, similar things, but you can essentially use different internal functions for dimensionality, for grid and the block. And then you use a parameter, the endpoint. This is really equivalent. It's just more, one is a better code than other ones from the programming perspective. And a kernel in the execution in a nutshell. So what happens is when I execute this piece of code, right here, it runs, it goes here, and that's what the host invokes. And then when the data arrives, this kernel block is executing this code, right? First this, and then the other one. Okay. So this is, I'll just leave this slide so you can read more about declarations, how you see code, like a coder would understand what is in the device, what is in the host, what is global. All these definitions are now needed because you have heterogeneous systems, right? So, I mean, host is clear, right? Device is clear. What global means is executed on the device, but only callable from the host, right? So this is like, allocations, for example, yeah.
It's funny because it's like nightmare notation to add two numbers, and then NVIDIA is saying that it's like general purpose compute, like.
Yeah, I mean, I had I remember I had a huge fight with Bill Daly on that when I just make comment on one of his talks saying this thing is not general purpose. And there was like a huge fight. Like he doesn't want to take it like lightly. He said, no, like general purpose, it's amazing. CUDA is amazing. It's very easy to program. Everyone should program just in CUDA. Anyway, so this is the flow of doing it. But by the way, I don't have anything personal against GPUs right now. Like hardware accelerators is the only way to go into the future, right? So we have to do it, but we just need to be honest about what we do. And sometimes when when you're too much involved into the company, you forget your academic hat and you're taking your industry hat too seriously. So you become biased, right, towards what you want to push the world into, right? Okay, so essentially what happens, you write this code that I showed you before, and then the flow is like that. You go through an VCC compiler, right? And then there is two interesting things happens. The code is not, again, thing to note. At the end of the day, this is two different devices. So compiler combines the host code for your CPU, and there's a linker, and then there is also device code that now needs to execute code that GPU understands, which is called PTX. Again, I'm oversimplifying it. It's really not the native ISA of the GPU. The real native ISA is proprietary, but what we can program as the users, the assembly that's visible for us is PTX, right? Or like PTX++ right now. And that what is then, compiled using device just-in-time compiler, right? And then it's executed on the heterogeneous platform. Remember, these two things execute on different devices. They need to talk to each other. This is like the compiler need to make sure this is all nice and smooth. Okay, here there are some details about multi-dimensional grids. This is really, as you want to execute more and more complicated stuff, is how to compute these indexes, right, of the block and thread. I had to be honest with you, like whenever I see in videos, like I've seen those slides many times, I still get confused which dimension is which. Nothing feels intuitive in those presentations to me, maybe because we didn't learn how to program in 3 dimensions easily. But anyway, so essentially the best way to think about it, it has a fixed type of 2D grid, but say your input or your output are not necessarily nicely aligned with that. So you would have to, allocate some partial things here and there. Another interesting aspect you need to think about when you're going to work about what is the layout in the memory, because it affects locality. Again, something, so CUDA follows the C++ row major layout. So essentially the last dimensions is the one that's the most local. So when you have A, I, J, right, it's like it's better be that you're iterating over I and then over J, not the other way around. Yeah. So then you had row width and column. This is how the memory is allocated. And essentially this is how the memory really stored and then how the indexing are allocated. So the index 9 means 2 multiplied by 4 plus 1. So it's 2 by 1 index, right? So this is the best way to think about this array going into that form and then into this scalar form, right? So this is how you collapse a 2D array into a single dimension, right? In row major order, right? Okay, so this is some example of the scaling function when you try to scale the pixel by 2.0 across the full image. So this is how the code would look like. This is there, as simple as it can get, and you see there is if conditions still here. It's hard to write a lot of code without any if conditions at all. Okay, and this is the host code that's needed to launch this kernel. So remember, this is a device code, right? Runs on the GPU. This is their host code that has both the, these invocations of the device code and also some allocations of the dimensionality that are either host functions or global functions. Okay, and as I said, not all threads in the block will follow the same control flow path, so that might complicate, convergence. And one issue is that here I'm showing you when the dimensions are large, much worse situation when the dimensions are small, because then you get huge underutilization. Okay. So that was a very fast summary through their programming GPUs, like some very basic examples. And hopefully you get the main principles, right? How the heterogeneous system needs to program, that it has different address spaces, right? That it has the code that can run on the host, on the device, on both, right? Just invoking from one side, but running on the other side. That you always need to manipulate GPU, and it can be programmed in a certain restricted way. So some algorithms that are super parallel, easy to program this way. A lot of algorithms are not, right? And that's just the given. And no matter which camp you are, whether it's general purpose or not, the takeaway is that's the only way to program it right now, right? A lot of things across the GPU stack is obviously proprietary, but you're given enough API to program, libraries. And NVIDIA built a lot of libraries for you. So in practice, you're not going to do vector additions or matrix multiplications. This is all very optimized and done for you. Okay, questions? I know it was a lot of information, but hopefully you learn a lot about GPUs today. If you never programmed them before, at least you feel in on how it can be. The best way is to program some of them. Mustafa? Oh, yeah.
Nothing.
I have a question. Does the dimension of grid and the block influence the performance of the program?
Yes. So it might, and there are two aspects. There is the more coarse grain, the bigger you are. There are like the trade-offs here. The bigger the chunks and the granularity of the grid, the less overhead of supporting the full grid. But if the input dimensions are tiny, right, then when you try to map those kernels onto this big grid, you might get huge underutilization. So there are tons of examples from ML that you should be familiar with. If you're dealing with like LSTM models that had a very small dimensions, and you start to map them onto these kernels, right, in this hardware, you ended up having a lot of underutilized threads, right? So you have functionality.
I mean, if the X, Y, and Z, can I use only a single dimension of the? For example, I only use the X to achieve the same performance.
Your goal when you draw different dimensions to get as many thread blocks as possible to write. So sometimes there's a whole lot of black magic hand tuning happens when people experiment with different dimensions, trying to get, because you pick these dimensions, then you would need that many registers. That may lead to 3 thread blocks, but then you manipulate with the dimensions, and you might end up fit a little bit more under other dimensions, a little bit better. And then you might run 4 thread blocks. At the end of the day, you get like a running ticket. You get thread blocks. So depending how you pick dimensionality of your problem, you might run different number of thread blocks.
Oh, okay.
So
I have another question.
Yes.
It seems that the CUDA can also call the function, and it seems that it need to maintain the function stack on their context. Where did they put this data in the device?
Yeah. Just to be honest, I don't know the precise answer. My expectation that it's going to involve host one way or another. So it's you write the code, right, in CUDA, but then it's compiled to something. I would expect there is some manipulation done by the compiler. So the best way to get the answer precisely is to take your example with an extra function call and get an VCC calling on it, right? And then see what it synthesizes as a PTX, right? I would expect there's going to be some context saving happening, and there is nothing else other than that. Although you might implement it maybe with a scratch pack, but I doubt it. I think it's going to probably copy in and out things or try to inline things. So they are gonna, like, compiler is gonna try first to avoid this function call. It's very bad, right, for GPU. So properly, it's probably gonna try to inline, and whatever it cannot inline, you would have to deal with some other ways.
Oh, okay.
Yeah.
Thanks.
Yeah. Like all these abstractions from the CPU world are not particularly amazing for GPU execution that just wants to execute the plain computational code, right? So it's kind of try to get rid of all of it, just focus on computation. That's my expectation. But I guess Serena might answer it right away. I would need to check. So I need to run NVCC to see what's synthesized.
So I guess you were saying that depending on the dimensions, like your running ticket, so to speak, is the number of thread blocks. Like, is there no way to just like directly specify how many thread blocks you want, or like, is that not exposed?
I might specify, but what if you don't have resources to run it? You don't have registers.
I see.
That's a problem. And you don't know, they know, right? Like you can only hypothesize how many registers you need, and they will try.
Makes sense.
And there is a virtual register that you see in PTX, but there's architectural register that hidden there that you don't know and have access, and you don't really know, right? So it's all hidden from you. So you kind of try different combinations. There's some rationals. It's not like completely black magic, but it's not a very straightforward process. And you might be slightly, like, you change, like, why is the biggest nightmare was dealing with accelerators. So someone worked in one company, wrote a lot of fancy CUDA code, and they retired or left the company, and you join and you get all this code inherited. And then, you know, CUDA changed and the new GPU arrives. The code runs, right? More or less, but performance sucks. And then you're like, okay, what is that he means by that dimension and this dimension here, and like why is it running poorly? Because it runs, but it runs really poorly. And then like you're trying to figure out the dimensionality and how you shrink things, and it's all in 3 or 4 dimensions. So it's like when you try to do combinatorial exploration of different hyperparameters, your head explodes very fast. So
I'm guessing there's like at least one paper that tries to just throw machine learning at the problem and try to guess the best number of dimensions.
yeah, well, I'm pretty sure people propose throwing them out of that, yeah. So it's won't be surprised, but it's a difficult problem because the search space is very non-convex. So a little tiny flip of one parameter, and then you get more thread blocks or fewer, and the performance goes up and down by like 30% easily. Yeah. Okay. Any other questions? Okay. Thank you, guys. Then. And yeah, I'll promise to get your feedback on the proposal soon. Thank you. Bye.
Thank you.